In this video, we're going to quickly talk about how to set up this problem involving Faraday's law and an RC circuit. I'm going to jump right into identifying what are our known variables, and then we will fill in kind of what we're looking for, how we plan to find it, and why we're going to use the equations, which I have already listed over on the side. This should be all the equations that we need. So let's take a look at what we know. So we are told the voltage of the battery, because we definitely have an RC circuit here. We're told the resistance. There's a single resistor in our RC circuit. There's also a single capacitor. Of course, that's going to relate to our time constant. We're given a time. It's got a subscript of 1, so it's implying we're going to have another time. Indeed, this is a situation where we're going to charge the capacitor for the T1 time, and then it's going to discharge for a time T2. Then we get on to our second circuit, which to look at it isn't much of a circuit, but it is a closed loop after all. And that's all it is a rectangular loop with 16 turns. So let's go ahead and identify that we have an N of 16. And we also know that the internal resistance of that second circuit is 2.07 ohms. Okay, then we are given some distance values. So involving the second circuit, because we're going to be interested in magnetic flux, we need to know the area enclosed by it. So essentially what we're looking at here is the area enclosed within that rectangular loop, which of course doesn't touch the other circuit. It's going to get a current through electromagnetic induction, hence the mention of Faraday's law. But anyway, we are told that it has a length, which is its horizontal side. And then we're given these two values, A and B, to place the loop a certain distance away from the wire. That's really what A tells us. And then B tells us it's the upper limit, but also the far side of the rectangular loop from the main circuit, from the RC circuit. And I'll probably refer to the loop that's going to have a induced current just as the inductive circuit. And then I will refer to this as the main circuit or the main RC circuit or the RC circuit. All right, so the two circuits are going to interact. Then we are told our last value, if I remember correctly, our last known, which is T2. I already mentioned that that's going to be the time that the capacitor is discharging, because we're going to charge it and then discharge it. I also give a bit of a hint down here. I won't go over that now because it's going to come up naturally when I start using the equations I listed. But let's go ahead and actually finally take a look at what we're looking to find, which is the current. So we want to find the induced current in that simple inductive circuit. All right, great. Well, let's get to it. And one last equation, since we are finding the current and not just the voltage that shows up in the inductive circuit, we are going to need Ohm's law. So I'll go ahead, which we already have a version of, but we need a slightly different one. So I'm just going to call this I induced, and it's just going to be V induced. And I am just interested in the absolute value of it. I don't care about the direction here, other than if I was specifically asked for it, but the current's going to be the same value regardless of whether it's going clockwise or counterclockwise. And then we'll put in our R value. All right, so let's go ahead. It looks like I don't specify between the two R's. So let's go ahead and call this one R1. All right, and then that's the resistor in the RC circuit. And with that notation, I will go ahead and call the internal resistance, which comes from all the wires, R2, okay, in the inductive circuit. And let's go ahead and drop our subscripts where they need to, because the time constant is going to be in terms of R1, the RC resistor, as is going to be that initial current value. And those are the only times that it's listed. Okay, because obviously tau shows up quite a bit, but at least 2 times. However, that tau is in terms of that R1. All right, so this basically comes down to putting everything together, thinking about what is the calculus ideas that come up, and there are 2 of them. One is that we're going to need to integrate to find the magnetic flux inside of the loop, and then we're going to have to take the derivative with respect to time, um, and that's going to finally give us our induced current. Okay, I'm probably jumping around a little bit, so we'll go ahead and get started. So let's have just kind of a quick summary in terms of our order of operations. Think of each of these circled numbers as just being a step. So step one, right? What do I want to do in step one? Well, since I'm going to charge the circuit for a certain amount of time, I need to find out what is my initial voltage on the capacitor. And I was just looking at my notation down here with my hint, and I have a CO. So let's go ahead and be consistent there. So we're going to have a value of C, or our notation C, and then a CO as well. The equations are mostly listed in the right order, but since I kind of filled some in, as I just did, in terms of ones that I may have forgotten, they're not exactly in the right order. Okay, so the very first thing we need to do is actually pretty far down the list, kind of in the middle of the list, and that's just going to be to find the initial voltage on the capacitor. So the initial voltage on capacitor after time t1. All right, and so that's just going to be charging up the capacitor. So that's going to be the equation I mentioned just a second ago. The capacitor would continue to charge until it reaches the voltage of the battery, and then it won't charge anymore. I don't think we're going to hit that voltage, and we never would hit it exactly. It approaches it, but our idea is the same. Okay, so we have everything ready to go to plug in there. Of course, we'll have to find tau, and tau is just in terms of R1C. No worry about equivalent resistances or capacitances here because it's just one of each. So you should be good to go to find out what the voltage is on the capacitor after T1 time of charging it, which is after 2.44 seconds of charging the capacitor. Taking a quick look at our values, we have a huge capacitor, 714 farads, and then we have a resistance that's on the order of milliohms. So it looks then that our, probably in the 10 or 20 seconds is going to be our time constant. So we're definitely, our T1 is going to be a significant fraction, but not a huge one. Okay, so anyway, we should be all good to go to find that initial capacitance. And last thing I wanted to say on that is that that's just when the circuit is consists of the switch being closed at point A. So the circuit would just go around like this, to go all the way around, and that is the charging circuit. Okay, but after T1 of charging, we now are going to start the discharging. So as far as the discharging, we're not going to, find a particular value. Let's see, because we want a rate of change. Let's see. So let's think about that. So if I want to find a rate of change, I guess the thing is because I need to know what the current is at that instant, as well as what rate it's changing at. So that's certainly going to be relevant. Let's see, because I say find the current in this second circuit. Yeah, but we won't plug in that time right, until we're done with the operations. And so what I had to kind of think of, and this is a common thing in calculus, and it kind of it can throw you off a little bit because it's different than what you would do in an algebra only approach, is that you have to take care of whether it's integration or derivatives to get your function, because you're essentially getting a new function with those calculus operations before you plug in your time. So even though you might think that we have an equation right here that has T1 in it, I almost wish I hadn't, rather up here. I almost this is our expression that has T2 in it, which is the T I'm referring to. I almost shouldn't have put it there, because it makes you think that you plug in the t, and you just find some value of current. But we don't want to do that. Instead, we care about the rate of change. And once we have a new function that's the rate of change, then we'll plug in t2. So let's go ahead and actually just leave this as a variable t, because as the equation's written, we're only going to use it as a variable. So just take off the 2 there. Okay. So let's go ahead and consider what we know. One thing that we do need to find is the initial current coming from the discharging capacitor. It's an easy step, but also easily overlooked. So we're just going to find the initial current through, I said, coming from, but it's also passing through is a circuit after all. So, but the power source of the discharging circuit is the capacitor, since the battery's gone. So find the initial current through the discharging capacitor. Okay, and that's going to be the equation I naught equals VC naught over R1. Okay, because we found VC naught in the previous step. Okay, there we go. Looks great. And you can see that that value shows up right in front of the the equation for the decay of the current, which is that time dependence. And so it's you can think of that as our initial value, almost like an amplitude, but not really, because there's no oscillation. Just it's what it starts at before it decays. Okay. All right. So now I think we're going to jump into the calculus steps. One thing is that there's a clear order here with Faraday's law that is going to apply to just about any problem that takes a calculus approach to working with Faraday. And any problem that involves both steps. Sometimes you don't have to do both, but one of them is to do a area integral, so a double integral, to find the total flux through your enclosed area, because you have to have some enclosed area in order to have an induced voltage, because of that enclosed area. Then you take the derivative with respect to time. So integral first to get the magnetic flux, then the derivative with respect to time to get the induced voltage. So that means that our next step, in fact, will be finding the total magnetic flux through the enclosed area. So find the total magnetic flux through area enclosed by the small, I'll call it induced circuit. It never felt right to call it the inductive circuit. It's more like the whole process is inductive, but the one that is the response, calling it induced makes more sense. Okay, so find the total magnetic flux through the area enclosed by the small induced circuit, and it's not just going to be something we can just multiply the side lengths by, because the magnetic field is dependent on distance. So that means we're finally going to use the equation right at the top, the very first one that I wrote down, which is the magnetic field created by a wire. So this is the magnetic field lines that go around a wire, in concentric loops, and they tell us that the magnetic field gets weaker with distance. So we have a decay or a weakening of the magnetic field as we move away from the wire, and that's why we have to do a little bit of integration, but nothing too cumbersome, a pretty simple function, but an important step. So let's find our total magnetic flux. So let's think about our integral here. So we'll have x and y, and I don't have a clear notation showing those directions, but we can fix that. So typical x and y directions. And so our limits in the x is just going to go from 0, and not that it matters exactly where I put the coordinate system, but you can imagine, right there. So, starting at the origin, moving the x direction, our limits are going to be 0 to L. And then our limits in the y direction are going to be from A to B. And that matters because we don't want to set the bottom of, the bottom side of the loop to be 0 because we have this dependence, we have this weakening field that starts down here. So this needs to be our x equals 0. So if we consider we want our x equals 0 to be at the wire that's carrying the current from the discharging capacitor. And then I already said we want our y equals 0 to just be on the upper left-hand corner of our induced circuit. So let's fill in our limits. So I'm going to have a limit here. I'll put the y second. So this is just going to go from 0 to L. It's going to be a trivial integral. It's just going to be L. So we can pull that out in a second. But then I'll make the inner integral go from A to B, known values, as I stated at the very beginning of the video, and then our magnetic field. And I'm going to make it clear that our magnetic field is just going to be, oh, you know what? I realized I kept saying y when I meant x and kind of vice versa. Sorry for any confusion there. I'll be clear going forward. It's just going to be a function of y, all right? And then we're going to have, since the inner one is the y direction, it's going to be dy, and then dx will correspond to the outer limits, okay? Which I mistakenly called y. Let's go ahead and put our function in there. And that's going to be the one that comes from the magnetic field of a current carrying wire, assumed to be long enough that there's no effects, and we'll make that assumption. So A to B, and then our magnetic field has the form of mu naught I, and then 2 pi and y, okay? And then dy dx. Now, we're used to calling it r because it's radial distance, but I called the axis that goes in that direction of weakening field y, so in this case, it's y, all right? So it's just saying that the magnetic field is decreasing with a reciprocal relationship to y, okay? And everything except the y is going to come out of the integral. So when we take a look at this, we're going to have our mu naught. Now, our I certainly is not constant, right? It's a function of time, but it's not a function of y or x. So, with regards to y and x, it is a constant, so it'll come out. And then we'll have our 2 pi. And of course, when we do a antiderivative of 1 over y with respect to y, it's going to become the natural log. So we're going to end up with a natural log function from our antiderivative. And then it's going to be evaluated accordingly. And I can go ahead and I'll go ahead and show the steps real fast. So then we're going to have 0. I didn't show the other, the algebraic kind of setup steps because there wasn't as much to say. But then let's go ahead and change the inner one. So I'm going to write the antiderivative in here. So natural log of y. All right. And then our limits. So it was not 0, but a. So a to b. And then we have dx. And it's a good thing, too, because we can't have it start at the wire because it's undefined. And that's an issue, right? So we have to have two values, none of which are 0 when you're doing something like this because of that natural log function. And then the dx. All right. So I mentioned before that there was going to be that trivial integral. That's the x direction. That's just going to become L because there's no variation in the magnetic field strength in the x direction. So that entire expression will just become L. And if we take care of everything on the inside and kind of take care of the that outer integral as well, it's going to look like this. So I have our mu naught IL, and then the natural log of, and I'll give me some parentheses here. So the natural log of B minus the natural log of A. All right, and then quick cleanup, use the law of logarithms just to make it a little bit tidier. And that's going to give us our mu naught IL 2 pi natural log of B over A. All right. Okay, and that's it for that step. We don't have too much left. Now we are ready to use our derivative. So Faraday's law proper. All right. We're just going to take the derivative with respect to time. All right. So let's go ahead and show that step. Okay. I don't want to have to flip back and forth too much. So I'll put step 4 over here. All right. And this is just going to be find the induced voltage. So find the induced voltage in the, you guessed it, induced circuit. The induced in the induced. Okay? So then that's going to be the magnitude of our induced voltage. Again, we don't care about direction. And then d and with of the magnetic flux with respect to time, which means that we need to substitute something in for I. We need to substitute in the time-dependent part for I. So I will show that. So if we consider our induced voltage, and that we know the expression, right, without the aforementioned substitution, but we know the expression for the magnetic flux, coming from the integral, and all we need is to put in for I the time-dependent function that we were assembling up here to get our so this is going to be the initial value, and then the equation we hadn't used yet, but I mentioned it, which is not that one, this one, which is the actual decaying current. So let's put that all together. Okay, so I'm going to pull out some of the constants that are in that magnetic flux expression. So the things that don't need to be differentiated with respect to time, not the I, but the L, the 2 pi, and even the natural log of b over a, because nothing time dependent there. The area is not time dependent, right? It's only the magnetic field strength is time dependent. And then everything we have left is the I. So what does the I look like? Well, we know the I expression is this one here. And I already mentioned that we know I naught is VC naught over R1. So let's go ahead and write that. So I'm not going to write I naught, I'm going to write VC naught over R1. And then multiplied by e to the negative t, not 2, just t, variable. It doesn't become t2 until we're done with the integration. So it's t over tau. All right. So let's go ahead and, I lost my integral. So I was focused on pulling out all the constants, but we got to the point where we didn't have them anymore. So let's actually have our d over dt here. So here, I'll just put it, make myself a little more space and put it right here. So d over dt of just that part of our expression. Okay? So finally, the induced voltage will be, and when we take the derivative of an exponential, essentially it stays the same, but we need to do a chain rule, which is just going to pick up a negative 1 over tau. Yep. So I'd have a negative, which I don't care about in terms of just finding the magnitude, but let's go ahead, and since we are taking the absolute value, here, I'll kind of write like this. So you get the negative, but it's just going to disappear. So we have the negative, and then we'll have the mu naught L 2 pi. Let's put some of our other expressions in here. We have our VC naught. Then from the chain rule of taking the derivative of the exponential, I said it was 1 over tau, so tau will be in the denominator. So that would be R1 tau down there. And since tau is, R1c, I guess it would be called R1 squared c, right? But I'll just leave it as tau because it's easy. I think it's easy to think about it. Look at tau and remember it's RC, or just remember it's a time. And then, okay, so that was everything except the natural log. Okay, and then the derivative, which I already had the chain rule part that I put out in front. Well, what's left is just the original function. So there we go. All right. So now we evaluate that at t2. So and evaluate right at T2. Okay, so that's kind of that would be probably step 5. We're nearly done, so I figure I'll just squeeze in the last couple. And then the very last step is just to use Ohm's law to find the current. So then the last step, all right, use Ohm's law to find current in induced circuit. Okay, and so then that's just going to be our I, and I just call it I believe, going up my equations here. I induced, there we go, and then V induced over R. I realize I never closed my absolute value brackets. So we have I induced is then going to be what we got from that whole expression after we plugged in T2. So basically take this, plug in T2, make sure that you don't have any negatives, and not that it matters, but we're only interested in the magnitude. So at some point, drop the negative, and then put that value in there, put that voltage value in there, and then divide by the resistance. Oh, one thing that I just left off is the N. Luckily, I can squeeze it in front because it was not a single loop, but rather a kind of a coil, rectangular coil of sorts. So it is, which of course is more effective because it's a stronger current as well as stronger voltage. So there we go. All right, and that is our last step. But I should make it clear that that's R2, and that's it. All right, zoom out so you can see it all together. So there you go. 6 steps more or less to set this up. In turn, do a couple of calculus approaches here and apply some ideas of RC circuits and Faraday's law. Hopefully, it all makes sense. And everything else in a system like this is just variations on this theme. And questions like part B, asking for power. Of course, that would just be using the power equation, which is just the product of current and voltage, or something. Or you could be, for example, asked to solve for the time rather than be given the time. And in this case, the functions can be solved by hand because you certainly solve for t and go from there. All right. Well, thank you for watching. I hope it was helpful.